So in this video, I'm going to explain what the simplex algorithm is doing. And we're going to do this by working through an example so we can see what is happening. So the example I'm going to work with is we are going to maximize 2x plus y subject to these constraints. 3x plus y is less than or equal to 6, x plus 2y is less than or equal to 7, x is greater than or equal to 0, and y is greater than or equal to 0, the non-negativity. Okay, and what I've done is I have drawn the feasible region here. So let's make sure we label it. So this line here, okay, so the y-axis is x is 0, so that is x is 0, and the horizontal axis, the x-axis, is y is 0. Now this one that goes through 2 on the x-axis and 6 on the y-axis is 3x plus y equals 6. So 3x plus y equals 6. And this line is x plus 2y equals 7. So x, let me just give myself a little bit more space, x plus 2y equals 7. So they are the equations of those 4 lines. Okay? Now, the simplex algorithm, in a nutshell, this is what it does. It starts at the origin, so it must start at the origin, okay? And it starts at the origin, and when you're doing graphical linear programming, you consider the vertices of your feasible region. So for the 2x plus y, we would have a line coming in, and the first point that it hits in the feasible region is the point that I am interested in, that maximizes that value. Okay, so what the simplex algorithm has to do is it has to test the vertices. And what it does is it starts from the origin, and with every iteration, it moves along one of the lines from the origin to one of the vertices. So it could go that way, or it could go that way. And once it's at that point, it judges whether the solution can be improved. And if it can be improved, then I'm going to then travel along this line up to the next vertex. And then I test at that point, can the solution be improved? If it can be improved, then I need to keep going, and I'll go through another iteration of the algorithm to get to the next vertex, and so on. So it essentially starts at the origin and works its way around the feasible region, checking the vertices as it goes. It is an exercise in simultaneous equations. That is essentially what's going on. So when you solve simultaneous equations using the elimination method, that is essentially what we are doing with the simplex algorithm. Okay? So let's go through some of the steps first then, okay? So the first thing is that because we have these inequalities less than or equal to 6, less than or equal to 7, I must turn them into equalities by adding in slack variables that I introduced in the previous video. So rather than have less than or equal to 6, I need plus S1 is equal to 6. So I'm going to use S1 as my first slack variable. So S1, and for this one I'm going to add in S2 equals 7. So that S1 and S2 are slack variables. And I would make sure that I write that down as part of my answer. Okay, so if I introduce a variable, I'm going to tell the examiner that I know that that is a slack variable. Now, you don't need to add in any slack variables for these non-negativity constraints, so we don't need to worry about those. The only other thing that I'm going to do is the 2x plus y, I'm going to give it a letter. Okay, so quite often we give that the letter P, as in profit is being maximised, okay? So I'm going to write that's P equals 2x plus y. But I'm also going to do something with that as well. I am going to put it in what's referred to as the standard form, which is to move all of the variables onto the left-hand side of the equation. Okay, so I make sure that I take 2x and y from both sides and put it equal to 0. So now it is in standard form, and all three are in the same standard form format. So I have three equations. I have p take away 2x, take away y is equal to 0. There's a reason why I've left a gap. I've got 3x plus y plus s1 is equal to 6. And I have x plus 2y plus s2, let me just pop it here, is equal to 7. And these are the three equations, and just like you would in the elimination method for simultaneous equations, I'm going to number them 1, 2, and 3. Okay? Right. Now, let's take another look at our graph. So, for this equation here, 3x plus y equals 6, I'd like you to compare it with equation number 2. Because if 3x plus y is equal to 6, that's going to happen when s1 is 0. So instead of calling that line 3x plus y equals 6, I could call it s1 equals 0. Because that is where s1 would be 0. And in a similar way, for x plus 2y equals 7, that is the equation number 3 if s2 was 0. So this line can be called s2 equals 0. Okay? So you've actually got x, y, s1 and s2 equaling 0, and they represent your 4 lines on the graphical linear programming problem that we have. Now, where 2 of these lines intersect, okay, so where 2 of them intersect, we refer to those as non-basic variables. So at this point, at 0, 0, so at 0, 0, x and y are non-basic, while s1 and s2 are basic. Okay? Whereas if I am at 2, 0, then at 2, 0, that is the intersection of y is 0 and s1 is 0. So at that point, y and s1 are non-basic, whereas x and s2 are basic. Okay, so that is what's happening at the intersection. Okay, right. So that's just some of the terminology that we'll be using and you need to be aware of, but it'll kind of link in more when we've got it into working with the Tableau, okay? Right, so how does this algorithm work? Okay, well the first thing is that I need to decide on in which direction I am going to go. So remember, I start at the origin, and then I need to determine, am I going to go that way, or am I going to go that way? Okay, so how can I tell? Well, the way that you go depends on which way will improve my solution the fastest. Okay, well, I know that because I started off with the p being the 2x plus y, this is what I'm trying to maximize, yeah? If I travel along the x-axis and give myself an x value first, I know that that will improve p faster because I'm multiplying it by 2. So whatever x value I have, I'm going to multiply it by 2. That would be faster and increase faster than if I was just multiplying by 1. So 1 lot of y. So it makes sense to go in the x direction. How can I identify that? Well, that is because the minus 2 that I have is the most negative value. So I use the most negative value, and that identifies from my top row, the most negative value identifies which direction I'm going to go. So I'm going to improve in the x direction first. So I'm going to look at that. So x direction. Okay. The next thing is, how far along the x-axis should I go? Because I need to stay in the feasible region, okay? I don't want to go out of it. And there are 2 lines that intersect the x-axis. We have the S1 is 0 and the S2 is 0. Which one am I going to hit first? Well, because we've got the graph, we can see it. We know that we're going to hit that one first before we hit that one. But when you're talking about 3 or 4 variables, you don't know. Okay, it's not going to be as obvious. So how can we determine that? Well, we need to figure out where that point is. So I figure that out by taking the right-hand value, 6, and dividing it by the coefficient of x that I have. So 6 divided by 3. So I would do 6 divided by 3 is equal to 2. Okay? Or I'm going to have the right-hand side 7 divided by the x coefficient 1, which of course is 7. So which one am I going to hit first? Well, I'm going to hit the 2 first before I hit 7. So 2 is the one that I want, and that identifies that the 3x is the one that I now want to work with. Okay, so in the tableau that we work with, the 3 would become what we refer to as the pivot. Okay, so this would be my pivot, that value. So we go through that process of determining which direction I'm going to go, and then which x value am I going to hit first. Okay, we do those 2 steps, and then we go, right, okay, so what are my values going to be at that point? So I'm just going to get around that, okay. So I'm going to have 3 new equations. So I'm going to have equation 4, equation 5, and equation 6. Okay, now equation 5 is going to be the new equation 2. Equation 4 is going to be the new equation 1, and equation 6 is going to be the new equation 3. So 1, 2, 3, 1, 2, 3. Okay? Now what you're looking for is you want to make the coefficient of x here in equation 2, for my new equation 5, you want to make it 1. So I divide through by 3. So I'm going to get x plus 1/3 y plus 1/3 s1. Just make sure I don't make any mistakes. And is equal to 2. So I divide that through. Okay. And then, once I've got that, I am going to use equation 5 to eliminate the x's from the other 2 equations. So just like you do with elimination method in simultaneous equations, I'm now going to eliminate the x's that I have here in equation 1 and equation 2. So for equation 1, what I need to do is because I've got the minus 2x, I'm going to have to add on 2 lots of this equation to eliminate the x's. So I'm going to have equation 1 plus 2 lots of equation 5. Now the p will just remain as p. Minus 2x plus 2 lots of x is going to be 0, so that's gone. Minus y plus 2 lots of 1/3 y will leave me with minus 1/3 y. So minus 1 plus 2 lots of 1/3. So minus 1 plus 2/3, essentially. I've got nothing plus 2 lots of 1/3 S1, so I've got plus 2/3 S1. Nothing plus 2 lots of nothing. 0 plus 2 lots of 2. So I now have 4. Okay, so the x value has been eliminated from equation number 1. So now I want to eliminate the x from equation 3. So I would do equation 3 take away equation 5. X take away x is 0, so that's gone. 2y take away 1/3 y would leave me with 5/3 y. I've got nothing. Take away 1/3 S1, so take away 1/3 S1. S2, take away nothing, so plus S2. And 7, take away 2 is 5. Okay? Right. So now, what has happened is we started at the origin. We are now at this point here. We have moved 2 units to the right in the feasible region. How do I know that? How do I know that that's what's happened? Well, at that point is the intersection of S1 being 0 and y being 0. Okay, so if S1 and y are all 0, okay, all of that bit is 0, and I have x is equal to 2, and S2 is equal to 5, okay, S2 is equal to 5, okay, that won't make much sense at this point, but we've got the p being equal to 4, because p was equal to 2x plus y, wasn't it? The y is 0, the x is 2, so 2 lots of 2, the p is 4. Okay, p is 4, x is 2, the S2 is 5, and the y and S1 are all 0. At that point, y and S1 are non-basic, whereas the x and the S2 are basic. Whereas previously, the x and the y were non-basic, whereas the S1 and S2 were basic. Because at the origin, we had S1 is 6, S2 is 7. Okay? So, that is how they have changed. And what you can see is that as you move, that is one iteration of the simplex algorithm. What it does is it has swapped x from being non-basic to basic. And it has swapped S1 from being basic to non-basic. So every time you do this, it swaps a basic variable for a non-basic variable. They swap around. Okay, and they go from basic to non-basic goes to basic. So that's what's happened. Now, are we at the best solution? That's the question now. Are we at the best solution? Well, how can we tell? Well, if I take that equation that we've got there and I rewrite it, so I move the y bit and the S1 over to the other side. P is equal to 1/3 y, take away 2/3 S1, plus 4. That's what I'm currently seeing. Now, if y here is positive because I've got a positive coefficient, that means that potentially p could increase. Because if I increase y now, p would increase. But the problem is, what about S1? Because if I move, the y might increase, but the S1 might also increase. And I don't want that to happen because that's taking away 2/3 S1. Because as that one increases, if that one increases, both might cancel one another out. So I don't want that to happen. So essentially what I want to do is I want to make sure that S1 remains 0. If I can make S1 0, then I can increase the y and it will increase my profit, increase my P. Okay? Right. So I want to keep S1 as 0. So that means from this point, I want to travel along the line S1 is 0. So I want to keep S1 as 0 by travelling along that line, and I want to get to this point here. So travelling along that line will increase my y value. So how can I tell, just from looking at this, that the simplex algorithm hasn't finished? Well, I can tell that because there is a negative value in that top row. Because there's a negative number in front of the y, I know that actually I may be able to do better and I may be able to increase my profit. So that is where I go next. So I am looking, so previously we looked at the most negative, and this now is the most negative. So I'm looking down this column. Okay? So, looking down this column, what we need to do is we need to figure out, am I going to reach this point first, or am I going to reach this point first? Now, with the graph, it's obvious. But remember, in 3-4 variables, we don't necessarily know. So, what I need to do is I look at the right-hand side value, so 2, and divide that by the coefficient of y, which is 1/3. So 2 divided by 1/3 is 6. And I look at the 5 and divide that by the 5/3. Now 5 divided by 5/3 is the same as 5 times 3/5, so that's 3. So clearly I'm going to hit 3 before I hit 6. So this is the one that I want to use. Okay, this becomes my pivot. Right, okay. So equations 4, 5 and 6 are now going to become equations 7, 8 and 9. And I'm going to start off by looking at equation 6, and I want to get this as one lot of y. So I'm going to divide equation 6 through by 5/3. So y, 5/3 y divided by 5/3 is just going to be y, and I want it to line up still. Minus 1/3 divided by 5/3 will be minus 1/5. So minus 1/5 S1. And S2 divided by 5/3 will be 3/5 S2. And I'm going to run out of room if I'm not careful. So let me just give myself a little bit more room. Okay, so 5 divided by 5/3 will be 3. Okay, doing this without a calculator, so just needed to be a little bit careful. So we've got that one. And now I use this equation to eliminate the y's from the other two, from 4 and 5. So what I'll need to do to eliminate this y here is I'm going to need to add on 1/3 of this equation. And it's 1/3 of that equation because I'll have minus 1/3 y plus 1/3 y. So that plus a third of that. So P will remain as it is. Okay? I've got nothing plus nothing, right? Minus a third y plus a third y. It's gone. 2/3 S1 plus 1/3 of minus a fifth S1. Right. I'm not trusting myself. So 2 divided by 3 plus 1/3 of minus a fifth. Okay, 3/5. So 3/5 S1. Okay. And we've got nothing plus 1/3 of 3/5 S2. So that's 1/5 S2. And then we've got 4 plus 1/3 of 3. So that's 4 plus 1, so 5. So that's equation 7. Right. Now for equation 5, I want to eliminate the 1/3 y, so I'm going to have to do this equation, take away a third of equation 9. Okay, so x, take away a third of nothing, so I've just got the x. I've got the 1/3 y, take away a third of y, gone. I've got the 1/3 S1, take away a third of minus 1/5 S1, so plus a 15th, so 2/5 S1. Okay, and then I've got the S2, I was running out of room then. I was right. Okay, so I've done that one, haven't I? And that's gone. So I've got nothing, then take away a third of that one. So I was looking at the wrong row. So 1/3, I've got nothing, take away 1/3 of that one. Oh dear, oh dear. It's easier when you're doing it on paper, trust me. On a whiteboard it can be a bit challenging. And then we've got 2, take away 1/3 of 3. So 2 take away 1, so I get left with 1. Okay, right. So at this point, I am now here. I am now at that corner, at that vertex. At that point, the S1 and S2 are non-basic, because that is where those two lines are intersecting, S1 and S2. So S1 and S2 are non-basic, whereas X and Y are basic. You can also see from this that X and Y are basic because X and Y are by themselves, whereas S1 and S2 now have all this other stuff in front of them. So the S1 and S2 are both 0 because that's where those two lines intersect. So I've got S1 is 0 and S2 is 0. Whereas the X and the Y, if they're both 0, all of that is 0. The X would be equal to 1 and the Y would be equal to 3. And the P, because S1 and S2 are 0, is equal to 5. Now, is that the optimum solution? Well, if you take that top row and rearrange it to get P is equal to 5, take away 3/5 S1, take away 1/5 S2, then you can see that if I increase S1 or S2, then what's going to happen? Well, my p-value is going to decrease. It's going to be lower than 5. The best that this can be is if S1 and S2 are both 0. So there is no way that I can improve that. And I can see that I can not improve it by the fact that there are no negatives in that top row. So this is definitely the optimum solution. Okay, that is as best as I can get it, and it occurs at those values there. The X and Y, remember, are basic. The S1 and S2 are non-basic at that point. This is what the simplex algorithm is doing. Okay, this is what it's doing. You start off from 0, 0. It has to start at 0, 0. Okay, simplex algorithm has to start there, and then it moves along either in that direction or that direction, depending on your feasible region. Okay, it might go diagonally, but it's going to move along your feasible region to the next corner, determine whether it can be improved or not, and then move to the next corner if it can be improved by moving. Okay, that is the simplex algorithm. We are going to now work with it in a tableau. So I'm going to work through this same problem, so it's with exactly the same setup and numbers, but this time using a tableau, so you can see how we actually set it out on the page rather than using the setup with simultaneous equations for the x's and y's. Okay, so we'll see that in the next video.